Explosions, high-speed impacts, shockwaves. These are forces that can level entire buildings and literally reshape the world around us. And they happen in microseconds. That's 1,000 times faster than you can even blink. So how on earth do you study something that's over before it's even really begun? Well, today, we're going inside the blast to pull back the curtain on the incredible high-tech toolkit scientists use to capture and understand these incredibly violent events.
So here's what we've got on tap. We're going to start with the biggest hurdle of all, the unbelievable speed of it all. Then, we'll dive into the tools scientists use to measure a material's breaking point, see exactly how it shatters, and even recreate these monster blasts safely in a lab. And finally, we'll look at the amazing new frontiers this research is opening up. Okay, so the first major problem for any researcher in this field is just the sheer overwhelming power of a shockwave. We are not talking about the slow-motion videos you can get on your phone. No way. These are events that are born and then die in a tiny, tiny fraction of a second, all while unleashing forces that can just tear through solid steel. How do you even begin to study that? And yeah, that right there is the central question. It's the one that has driven decades of incredible innovation. And to answer it, scientists have had to invent a whole new set of tools, each one more clever than the last. So let's take a look at the first one. Think about it. Before you can build stronger armor or safer buildings, you need to know one absolutely crucial thing. What is a material's breaking point? When a shockwave hits it, what actually happens? Does it bend? Does it just shatter into a million little pieces? Or does it hold strong? To find out, you need a way to measure its strength under the most extreme conditions you can possibly imagine. To get that super precise data, scientists turn to a device called the Split-Hopkinson Pressure Bar, or much easier, the SHPB for short. The best way to think of it is as the ultimate high-tech hammer and anvil. It's designed to deliver one single, perfectly controlled, high-speed impact to a tiny sample of material, and that tells us exactly how much force it can take.
So how does this thing actually work? Well, it's pretty ingenious. As you can see, a small sample gets sandwiched between two long bars. Then, a striker bar hits one end, sending this powerful stress wave rocketing down the line. As that wave passes through the sample, super-sensitive sensors precisely measure how the wave gets altered. And that change, well, that tells scientists everything they need to know. It answers that one fundamental question: how strong is it? So knowing a material's strength is absolutely critical, but it's only half the story, right? Scientists also need to see what happens during that microsecond of pure chaos. How does a failure even begin? Where do the cracks start to form? For that, we need to move from measuring force to actually capturing the impact itself. And this is where things get really, really cool. This tool is called VISAR, which stands for a very long, very technical name. But all you really need to know is that it's basically like a cosmic speed gun. It fires a laser at the surface of a material, and as that surface gets blasted outward by a shockwave, VISAR calculates its velocity with mind-boggling precision. So while the SHPB tells us all about strength, VSISR gives us a totally different piece of the puzzle. It's the tool that answers the question, how fast is the surface deforming and moving? This data creates what's called a velocity profile, a perfect timeline of the shockwave's effect on that material. But what if you want to actually see the cracks form in real time? I mean, with your own eyes. That's where high-speed imaging comes in. Using incredibly fast, synchronized cameras and techniques like digital image correlation, or DIC, scientists can basically create a slow-motion film of the material breaking apart, frame by devastating frame. And in an image like this, you can see exactly what I'm talking about. See, high-speed imaging isn't measuring velocity like VSAR. It's capturing the raw, visual evidence of failure. It answers the question, how does it break? You can literally watch the fracture lines spreading across the surface, giving scientists a whole new level of understanding. Okay, so let's put these two side by side so it's really clear. On one side, you've got VISAR, which is all about measuring velocity. On the other, you have high-speed imaging, which records the visual deformation. One answers how fast, and the other answers how does it look. And when you put them together, well, you get a comprehensive 360-degree view of what's happening in that split second of impact. All right, so we have tools to measure strength and tools to see the impact, but where do the shockwaves come from? I mean, you obviously can't just set off explosives in the lab, so scientists need a way to generate safe, controlled, and repeatable blasts to test their materials reliably,
over and over and over again. And these are the go-to tools for the job. You've got shock tubes, which use compressed gas to generate a really precise shockwave, kind of like a controlled burst of air. For a little more power, they're specially designed explosive-driven devices that can be used in highly controlled environments. And all around the experiment, you've got an array of pressure sensors measuring the exact force of that simulated blast, capturing every last detail. Now, the crucial point here is control. The whole goal is to create what's called a planar shockwave. You can think of it as a flat, uniform wavefront, like a perfectly straight wall of force. This allows for clean, repeatable experiments where the pressure and impulse can be measured accurately every single time. It's really about taking the pure chaos of an explosion and turning it into reliable, predictable data. And this is where it all comes together. With this incredible toolkit at their disposal, researchers are now moving way beyond just testing simple materials. They're combining all of these methods to tackle much more complex, real-world problems. Everything from protecting soldiers on the battlefield to designing safer cars.
For instance, they're now studying how shockwaves affect the human body. By creating surrogate materials that mimic human tissue, they can use these tools to understand and hopefully prevent injuries from blasts. They're also simulating what are called combined threats, like what happens when a material is hit not just by a blast wave, but also by flying fragments at the exact same time. This is the kind of research that saves lives. And that really gets to the heart of why any of this matters. This isn't just about breaking things in a lab for the fun of it. The entire purpose, from the pressure bars to the high-speed cameras, is to use that knowledge to build better armor, safer vehicles, and stronger buildings, to ultimately, better protect people from harm. It really leaves you wondering, with these incredible instruments allowing us to see the unseen and measure the unmeasurable, what's next? What new materials, what life-saving technologies are just around the corner, waiting to be discovered inside the blast? The answers could honestly change the world as we know it.